Hi, everybody. So we got 3 more sections to go, and we're starting what's called power series. And the idea here is that everything we've done up to this point in chapter 11, we've looked at series of numbers. What we're going to do now is look at series as functions, and it's a big departure from anything you've seen before. So we still have to use series as numbers, as you will see. So let's get started. Okay, so a power series is anything of this form where it just looks like a big polynomial, basically, right? It's a constant, which is a coefficient, then times x to the nth power, and it's the sum from 0 to infinity, and you get this sort of infinitely long polynomial. So what happens is that you plug numbers in for x, and then you get either convergence or divergence, depending on what numbers you plug in. And so what happens is we can use the ratio test to figure out the range of values that converge, and then we check the endpoints with our other tests. And so we want to know, where does any particular power series converge? In the next section, we're going to see where each power series comes from and what it can do. But for now, we're just treating these as an abstract, infinitely long sum of functions. So the sum of the series, of course, is a function, right? You plug in x and you get f of x out of it. And the domain is the set of all x for which the series converges. So we got a few examples coming up. Hopefully it's explained pretty well. As always, let me know if you have questions when you're going over this stuff. Yeah, just remember, it's not a polynomial because there are an infinite number of terms. And it turns out we've already seen one kind of power series. It was the geometric series, right? All the c's are just 1, and it started at 0. And we already saw that if r is between -1 and 1, so in this case it would just be x, then it converges, and if r is greater than or equal to 1, it diverges. Right, we saw this one already earlier in the notes. Right, we saw that the sum of this was 2. And then here's just another sum that easily can be shown to diverge, right? Just use the divergence test. So this is just a nice sort of concrete example of some of the more abstract stuff we're about to do, because you've seen geometric series before. So if you're not really sure what a power series is, if you're having trouble wrapping your head around it, just remember it's sort of a geometric series type of thing, but with there can be functions in here, right, as you will see. So let's get started. So one thing you want to notice is that the function that's in here can really be anything, but it's going to be a function of n in here. It's going to be multiplied by x to the n. So the x to the n is a function of x. And then these other things all have to depend on n. As you can see, there's a lot of n's here. So we're just going to use the ratio test, right? So you plug in the an here and an plus 1 here. Now we can pull the n's and all the negatives. So the negatives go away because of the absolute value. And the n's can be pulled outside of the absolute value. Right, so I got rid of the negatives. And then here I pulled the n's outside of the absolute value. This we can simplify, right? This is going to be 1 plus 1 over n. This is just going to be x, well, absolute value of x. Now we can evaluate this limit. We just get 1 plus 0, which is 1, so which is just x. Now the ratio test, we're looking for convergence. The ratio test tells us that this will converge if whatever this thing reduces down to, In this case, it just happens to be x, but it could be anything. Whatever this thing simplifies to has to be less than 1. But we don't know about the endpoints, right? The ratio test doesn't tell us what happens when absolute value of x equals 1. So we need to check these endpoints separately. So what we do is we go back to our original series, and we plug the endpoints in, and they turn into numbers, and we see what happens to those numbers. So here's how it works. Here's our original series. Just take -1 and plug it in for x. Now all the x's are gone. We just have n's, and it looks like a problem from earlier in chapter 11. So -1 to the n times -1 to the n is just -1 to the 2n. Well, -1 to the 2n is always 1. So it just goes away. We're just left with n. Well, this diverges, right? These n's are not approaching 0. They're approaching infinity. So automatically diverges. Let's check the other endpoint. So we plug x equals 1 in. And here, -1, so 1 to the n is just 1. So it just goes away. You just have -1 to the n times n. But we can see this also diverges, right? These terms are not getting closer to 0. Even though they're alternating, it's just, it's -1 plus 2 minus 3 plus 4. That's not approaching any particular number. That also diverges. So that means both endpoints diverge. And so the interval of convergence is, it's what we got when we did on the previous page, but the endpoints are both open intervals because the endpoints are not squared off because it diverged at the endpoints. So anytime you have a problem where the interval is a number to a number, you have to check the endpoints. There's another example of that coming in a second. So we're interested in the most general type of power series where everything's the same as what we saw, except x minus a is in parentheses. So that's a horizontal shift. So this thing can be scooted up or down the number line. It's called a power series in a power series centered at a, or power series about a. They all mean the same thing. I usually say centered at a, but the book or whoever's speaking out loud could say it any of the three ways. And again, we normally use the ratio or root tests. Now it turns out when we evaluate convergence or divergence of these power series, only three things can happen. The series converges only when x equals a, and you can see from the formula why that happens, right? If you plug in a, you get a minus a, which is 0. 0 to the nth power is always 0. So there's no way it could ever diverge. It's not possible. The series could converge for every number x. That's something that can happen. We're going to see examples of each of these. Or there's a positive number r such that the series converges if x minus a is less than r, and diverges if x minus a is greater than r. So we saw that in example 1, right? A happened to be 0 in that problem. So we just had absolute value of x is less than 1, so r was 1. So r is called the radius of convergence. So in example 1, the center was 0, and the radius of convergence was 1 on either side, so it was -1 to 1. So when you think of radius, it doesn't seem like there's a circle there, but you can kind of imagine just a circle at 0 and its radius 1. Where does it touch the number line? At -1 and 1. That's not as weird as you might think. Those of you moving on to more advanced math, you will do these things with complex numbers, and it turns out it really is a radius because you have the imaginary axis. Now, in case 1, if the series converges only when x equals a, that radius of convergence is 0. It's just, I mean, it's not a circle, it's just what we call it. And in case 2, If it converges for all x, then we say the radius of convergence is infinity. It's just as big as you want. All right, let me put the whole thing up here. All right. So the interval of convergence is a power of a power series is the interval of all values of x for which this series converges. So this is really similar to the radius of convergence, right? Case 1 was the radius of convergence was 0. It could just be a single point. In case 2, the interval was negative infinity to infinity. So again, that corresponds to the radius of convergence, right? And in case 3, we can rewrite this as this. And then we check the endpoints. So in example 1, our endpoints were negative 1, right? Because A was 0, so it was 0, and R was 1, so it was 0 minus 1, which is negative 1, and 0 plus 1, which is 1. So we check the endpoints, negative 1 and 1. So the series might converge at one or both endpoints, or it might diverge at both. There's 4 things that can happen. You could have converge, converge, one converge, one diverge. There's lots of things that can happen. But in all 3 cases, the power series always converges at A. So that's important to remember. So the center, A is the center of the power series. It always converges at that point. You don't have to check it separately. All right, let's do another one. So for what values of x does this power series converge? Again, we're going to do the ratio test. And we're going to see what happens. So there's an plus 1. Simplify it as much as you can. So I just did flip and multiply, right? You're going to see that these 2's are going to cancel. We have an x to the n plus 2 and an x to the n plus 1. So one of those is going to, all except one is going to cancel. So we're going to get an x in the numerator. And then we're going to get it. Here's an n factorial and an n plus 1 factorial. That'll just be an n plus 1 in the denominator. Right? So I just rearranged everything. Simplified. Right? The 2's canceled. The n factorial and n plus 1 factorial canceled down to this. This canceled down to this. So you can pull the n's out of the absolute value. You cannot pull the x out. X has to stay there. But this limit is 0. So the way we think about this is you select x, and then you run the limit as n goes to infinity. So for any x you plug in here, this limit's eventually going to be 0, which means it's going to converge, right? We're doing the ratio test, so this we just have to check that it's less than 1. The absolute value has to be less than 1. Well, 0 is less than 1, always. So that means this particular power series converges for all values of x. So the radius of convergence is infinity, and the interval of convergence is negative infinity to infinity. That's supposed to be minus infinity. Minus. All right. So that's what it looks like when it converges everywhere. Let's see what it looks like when it converges nowhere. Notice here we're not centered at 0. Right, we're centered at 1. Ratio test again. So, same setup as you've seen before, right? There's an in the denominator, and then an plus 1 in the numerator. So you can see how everything simplifies, right? We have an extra one of these terms in the numerator, so it's going to cancel to this and stays in the absolute value. This thing here reduces just to n plus 1. I can pull it out of the absolute value. But no matter what I pick for x, this eventually gets bigger. So that means that this limit diverges. So for any x I pick except x equals 1, because x equals 1 is the center, this will be 0. This thing diverges, which means the radius of convergence is 0. And then for the interval of convergence, we write it as a single point. This is how you write a single point in math. You write it with curly braces. You don't write it as a closed interval from like 1 to 1. Don't do that. So we're going to do one more example, and then I'll kind of summarize everything. You might want to go back over this stuff before you try the homework. And as always, 90% of the problems I do in the notes are from the homework. All right, so here's the last example. For what values of x does the power series converge? So ratio test again, of course. Flip and multiply, and then factor out what you can, right? So the n's can all come out of the absolute value. The x's have to stay in. And then we're going to be able to simplify, right? 3 to the n plus 1 over 3 to the n is just 3. I can pull all these inside the radical. And this is just x. That's right, so 3. I combine this into a single radical, and then I can keep simplifying this. Right, this is just 1 over 1 plus 1 over n. Just divide through by the highest power in the numerator. This thing has to be less than 1, right? So this limit here is 1. So 3 times 1 times absolute value of x. So 1 times absolute value of x has to be less than 1. So this is the first time we've seen something like this, where this whole thing has to be less than 1, which means absolute value of x has to be less than a third. You have to divide both sides of the inequality. You have to get x by itself. So you divide this by 3, divide this by 3, and you get that. So that tells us our radius of convergence is 1/3. But we still need to check the endpoints. We don't know what's going to happen with the endpoints. So let's plug them in. So I always start with the negative endpoint. I just like to go left to right. There's our original series. Plug in negative 1/3. And then a bunch of stuff cancels, right? So 3 to the n and negative 1/3 to the n and negative 1 to the n. So the negatives cancel, right? Because it would end up being like negative 1/3 to the 2n, which is just 1/3. And then the 3 and the negative 1/3 are both to the n. Those also cancel. So this whole thing just simplifies to this. And this diverges. This is a p-series, right? Let's check the other endpoint. Same thing, plug in 1/3. Again, these two cancel, but this one doesn't. This one sticks around. Now we have an alternating series. So it alternates. So the alternating series test, all you have to show is decreasing and goes to 0. Well, this definitely goes to 0, right? As n gets bigger. So we're talking about the bn. The sequence of bn's has to go to 0. So 1 over square root of n as n goes to infinity goes to 0. We actually did this problem earlier in the notes. So this converges, but this is the alternating series test. And so we get this funny looking interval of convergence, right? On the negative side, it diverged at the endpoint, but on the positive side, it converged on the endpoint. So there were 4 very different examples we just did. Every problem in this section is a little bit different. And when you get to checking the endpoints, that's where you have to use the techniques that we saw in the previous section in 11.7. So there are many ways that a power series can converge or diverge. Problems that seem very similar can have very different results. So these don't look like vastly different types of problems, but it turns out they are, right? The radius of convergence was different for each one. The interval of convergence was different than each one. And some of them had single endpoints that converge. You might see some where both endpoints converge. You have to check everything. Alrighty, so there's the 4 examples summarized, so you can kind of just look at it to see what can happen. You might want to try these again before you try the homework. You don't have a ton of homework, but you will definitely be using these ideas in the next section. All right, well, that's it for today. If you have any questions, as always, let me know, and I will see you next video. Bye-bye.